Hi, my name is Christian Apollo, my teammate is Luis Pesante, and we're going to talk about the effect of harmonics in electrical networks.
Hi, I'm Luis Pesantes and I'm going to talk about harmonics in electrical network. In electrical power systems, the device and equipment that are connected to both by the company itself and by the customers are equipped to operate at 50 or 60 cycles per second with a sinusoidal voltage and current. Every current grid has a larger number of non-linear elements from the same mode with the frequency of the red. Other ways of different frequencies causing the phenomenon known as harmonic. Harmonics are sine voltage or currents that have frequencies that are multiple integers of frequency at which the power system is designed to operate. Distorted waveform can be decomposed into sum of the fundamental frequency signal and harmonics. In this slide, the red graph shows the fundamental frequency signal, the green graph shows the disharmonic, and the blue graph shows the consequence of the sum of the fundamental frequency plus the disharmonic. The harmonic distortion originates due to the non-linear characteristics of the equipment and loads connected to the power system. The harmonics are phenomena that cause problems both the users and the entity in charge of providing the electric power service, causing various harmful effects on the network equipment. There are several indicators that allow quantifying and evaluating the harmonic distortion of the voltage and the current waves. These are power factor, crest factor, distortion power, frequency electrode, and harmonic distortion rate. Limit of harmonics in Ecuadorian electrical networks. The level of harmonic distortion of the limit voltage is evaluated according to several parameters. First, VHK, voltage harmonic in H in the 10-minute interval of K. Then, VHI, a free value RMS of voltage harmonics measured every 3 seconds. DVHK, individual harmonic voltage distortion factor H. THDK, total harmonic voltage distortion factor. And finally, VN, nominal voltage and the measured point. Well, the maximum limits of limited harmonic voltage distortion and total harmonic voltage distortion are as follows. Low voltage, individual harmonic 5.0, THDH. Medium 3, and THD5. High voltage, individual harmonic is 1.5 and THD 2.5. And high voltage, in individual harmonic 1 and THD 1.5.
My teammate already explained you what an harmonic is and how it can affect electrical networks, but do you know how to mitigate them? Well, filters are commonly used to reduce or in some cases eliminate the effect of harmonics in electrical networks. There are many types of filters such as low-pass filter, band-pass filter, and high-pass filters. In this case, we're going to focus on the study of the reduction of harmonics using a specific type of low-pass filter, which is the receive filter, and its circuit is the one that is shown on the slide. Now, if we analyze this circuit using the Kirchhoff's law, we will obtain that the voltage of the source is the same as the voltage of the resistor plus the voltage of the capacitor, where the voltage of the capacitor is the same as our voltage of interest. Now, let's focus on this part. The voltage of the capacitor is directly proportional to the capacitive resistance, which is inversely proportional to the frequency. With this, we know that when we work with high frequency, the capacitive resistance will be slow, and therefore the voltage of the capacitor will also be slow. On the other hand, when we work with low frequencies, the voltage of the capacitive resistance will be really high, and therefore the voltage of the capacitor will also be really high, which will be almost the voltage of the source. Now, to continue with our analysis, let's get the equivalent circuit in frequency domain. In this circuit, we are able to obtain the transfer function of the gain voltage. This function is the reason between the voltage of interest and the voltage of the source. Now, if we want to obtain the frequency response of the filter, we only have to replace the variable S with JW. Now, with the transfer function, we are able to obtain our body diagram, but first we have to know how many poles and zeros our function has. In this case, we only have one pole with a cutoff frequency of 1 radian per second. With this, we know that for frequencies before the cutoff frequency, which is 1 radian per second, the voltage gain is 0, but after this point, the voltage gain will be a straight line with a slope of 20 decibels per second. On the other case, in our phase body diagram, a decade before the cutoff frequency will be 0, on the cutoff frequency will be 45 degrees, and a decade before the cutoff frequency will be 90 degrees, and then it will remain stable on this pattern. If we analyze the gain body diagram, we will know that for every frequency before the cutoff frequency, the voltage gain will be the unity. And after that, for every frequency after this point, will be lower than the unity. And this is the standard behavior of a low-pass filter. Thank you.